So if everyone is back and we are ready, let's get started. We stopped here on type variables. We talked about like types that are specific, such as bool, such as strings, list of things. But what's interesting is we also talked about like these variables, type variables. Actually, they call type variables that are indicated by lower cases, meaning they could get multiple types, not at the same time, but multiple types at once, in the sense that they are polymorphic. So that's why instead of being called a type, simply it's called a type variable, because it's a type that changes. And if you remember when we had the case where we have the num class, we said that if you are writing a function that adds two values, let me just switch here. If you're adding a function that has two values, let's see if I can figure this. One second. Can you guys see my screen?
Yeah.
Okay. You're seeing the repo one, right?
Yeah, repo.
Great. So again, here you have, for example, this function calculate sum that we talked about. And we said that, you know, when you then specify the types, in this case, we ended up specifying there. But if you don't specify that type, what you will get from Haskell, it's something like this. So instead of having an integer here, an integer there, and another one there, then being what the function gets in as a first parameter, second parameter here, and then last parameter, what it returns there, you will get this A, which generally indicates that A could be multiple types, not at the same time, but one at a time. It could be an int or it could be an integer. So those are called type variables, the types that, you know, change depending on the context. So if we go back to our lesson, and we're gonna come back to that. We did talk about you know, the first as one example of function that takes that doesn't take a specific type, because you have like those things, a tuple with one thing that could be int, integer, or whatever. You have b that could be anything, any type, and then the first function returns the a, which is the first element into this tuple. Yeah. So I just wanted to make sure that I stressed on that a little bit. So if we move on to functions, and if you recall, we defined functions as the core building block of Haskell, in addition to types. And we do have two concepts surrounding functions, which are functions declaration and function definition. You know, function declaration being how you give a type to the function. So you specify what goes in and what goes out, just like that in this caption, in this drawing. The function definition is actually what you do with what goes in. So you have to do some calculation with what goes in, and then you return some sort of result only based on what goes in. And this is really important because in Haskell, as opposed to other languages, object-oriented, you can get inputs into your function. They call methods in other languages. And you come up with an output or a result that doesn't just depend on those input, that depends on that input and some other stuff that are outside of the function. In Haskell, you cannot do that. And this is where the concept of purely functional language comes in, meaning that you have what comes out is what depends or is determined by what goes in. I will take one example here. When you're at home and you are grinding your peanuts, I don't know, we have something here in Cameroon called sauce dole, where you mix up like peanut with some sort of condiments, and you're grinding them. You're not going to get anything else than what you put into that grinder, if that makes sense. That's a little bit how you can see Haskell. So if we go back to the function declaration, what is a declaration? And we talked about this a little bit. So a declaration is basically something of this syntax, where you list out all the inputs to the function. You list out all the inputs that are going into your function. And it could be 1, 2, 3, and n. So as many as you need, although it's not recommended to add too many. If you have a function with too many parameters, maybe you should be thinking about creating several small functions and putting them. But anyways, you can have as many as you need. And then the last element on this writing here, where you have type 1, type of input 1, arrow, type of input 2, arrow, ... type of input n. The last in this being like this one here, the last, it continues there. The last being this one here, represent the thing that the function returns. Meaning if we have integer here, we have a list of string there, we have a char character there, and then we have a boolean here. It would mean that our function, or my function, that being the name of my function, takes in as parameter, what I just listed, and then returns the boolean as its result. So the last on the list is always the result returned by the function. So over here, we do see some strange writing, and it says constrained, and it basically means that here we can have some constraint on the data that are going in. If you remember with our function, let me go back here very quick and show you. So if you remember this, our calculate sum function, if I do this and I put it there, bear with me. Let's do that and make sure that it's the only thing we have in here that is visible. So what we're doing here is we are giving a declaration to our function calculate sum. Its name is calculate sum, and it starts with a lowercase. That's a rule. And down here, we have the definition of my function. So as you can see, these parts here represent what I call constraint on A. So you see, I'm saying here that A could be anything as long as it's a known. And we'll come back to that. Why I hinted that it's called type class. But here we have the first parameter of type A. It has type A, and it's called type variable because it can take many forms. And that's where we'll go when we try to execute this function. The second parameter is another type A. I will go there to that second parameter. And look, is I only work with these two values to figure out the type that I return, it being the result. So that's like the definition. That's all about the definition, the declaration of the function. Its declaration being its type, that is here. Its definition, it's how you actually get it to do the job it's supposed to do. And this syntax here just says that the function takes two parameters. We could have something else here, b. In that case, I will have to add another here to match that, val3. And the last parameter is whatever value the function returns. So are there any questions on that? Oops, sorry, sharing. Can you guys see my screen?
Yeah.
Yeah, we can.
Yeah.
Okay. So that's about the function. Let me see. Let's go back really quick. So that's what we have about this function syntax. I want to make sure that everyone, we all get this because it's really important. So down here, again, you can see that that's my function declaration. So I'm giving it a type. I give it a name. I use this construct. So my column. It takes an integer as first parameter. Takes another one, and then it returns that. And you can see here when I do its implement its definition, it's only using those two integers that takes into build a result. So here we have an example of a simple function. Again, if someone could tell me which part this is, that would be great. What does this represent? The thing I'm highlighting, first or empty. What is it for the function?
I think it's a bool.
Okay. Any other suggestion? So this is actually the name of my function. So remember, here it's the name, always the name first. And then obviously here we don't have a type, but we can see that this function is taking in something called LST, and it's running some check on it. remember we saw the null function, which checks whether a list is empty or not. It checks if it's not empty, it's returning the first element of that list by calling head, which is another function on that element. And if it's this guy is here is empty, it returns true, it will return empty. So that's what we get here. So again, I think most of this we will and make like examples, a lot of examples to make sure that we get all of this. So now, we've been talking about if, then, else as a construct. It's a way that helps us check if a condition meets a given property. So the if, then, else construct in Haskell will have a condition that we want to check here. So in this case, for example, we have a value that we have assigned 34 to, and over here we want to check if that value is divisible by 5, and there's an operator modulo that we saw early on that actually takes a value, another one, and figure out if the result of this operation is 0, meaning the remainder is 0 after I divide a by 5. In that case, it's it's divisible by 5. If not, which is the then construct, which is the result of this. So if this condition is true, because that equal would compare this value and that, and it will return either true or false. Then the then constructor will return 0. So if that's not the case, it will return 1. So very simply, let's make sure that we do this. We write a function that shows that. So I'm going to share my screen. So let's say we write a function called check if divisible by 5. So I want to check whether a given value or integer is divisible by 5. So we need to start with its declaration, meaning specify its type. So we'll take an int, and it will return, a bool. If the value of the bool is true, it means it's divisible by 5. If it's false, it means it's not divisible by 5. So if we do check, now we are going to implement its definition, and we're going to call whatever parameter is passed as first. We'll type int, we're going to call it x. We're going to say equal. So line right there. We're going to say if so parentheses are for grouping, some sort of calculation that I want to do. So we talked about the modulo function, which takes 2 things. It takes a number, in my case, what was passed here, and it takes another number, in our case 5, and it will return. So this is a function call, so this will execute and return something that I will then compare to 0. So if whatever thing this return is 0, then I will return true, because it being 0 means that x is divisible by 5. You know, and I will enter there. I will do my else. Else is the opposite of this. So this didn't return 0. In that case, what will I do? I will return false. False meaning that whatever value I entered here is not divisible by 5. So very quickly, let's go to the GHCI. And in there, we will load the main file. And once we have that loaded, our function is init, so I can just start typing and hit tab to complete. And I will pass in an int. So I'll do 5. Is 5 divisible by 5? There I get true. If I do 6, I expect false. And that's good. So that's the if and else construct. Any questions on the if and else construct? Take that as a no. Okay.
Sorry,
So,
I have a question. I'm going to try to write it because my environment is a bit noisy. Or I can just try to go on like this.
sorry, what was that, Asa?
I was saying I have a question, but there's a baby crying behind me, so I was just trying to. Anyway, I think it's okay. I can ask. My environment was a bit noisy. So from what I see, the if there looks very much like a function itself, in that it's returning a value.
Yeah, exactly.
So can it return value of different types, like the then and the else? Like if let's say the then is a number and the else is a character or something else.
No, actually, I think that's a great question. Because, you know, everything in Haskell is an expression at the end of the day. And if really is that construct is actually a function that will return the same thing. So because here we're checking a condition, and that then is returning that thing. So on the else branch, go accompanying the if, we have to return the same thing. So if we try to, you know, we have a happy case where this is true, and we return, let's say 0 here, which is an integer, and if not, we try to return a character, the compiler that really matters. So that's the possible. Really great question.
Thank you.
Cool. So let's do pattern matching. So again, very quick. You know, pattern matching in Haskell is really about like specifying, you know, some sort of like shape that a data or specific value that it has. So it's kind of like mapping the body of the function to a given parameter. And what it does is it allows us to really do neat stuff in Haskell, which are writing stuff like this, like where you have a function, for example, say me, that takes you know, integral integral values and returns like a string, and you are actually matching this pattern. So this is a pattern that you are matching, meaning that, you know, if this function is called and you are passing 1 to it, then the result should be 1. If it's called with 2, the result should be that, and so on. If it's called with anything else, you should return this. So what will happen is once this function is executed, it will go in that order. So it will start by checking if what you pass is 1. In that case, it will return 1, and it will follow that way. And once you give it something that doesn't fall within this pattern, it will return that. We'll come back to this, but an example of a pattern is, the factorial function, where you get an integer. That integer is 0. You return 1 as its value, as its result, and if not, you just return, whatever was passed to the function, multiplied by the same function, this time called with a smaller value of n, it being n plus 1, n minus 1. And this is, something we will come back to, recursion, but we want to focus here on the pattern, pattern matching, and making sure that the body of our function called with a given form or a given value of a parameter is used to implement the function, instead of using if-else statement that read a little bit, that are very difficult to read when you have a lot of them. So down here is another one where we have the cal function that takes in a list and return a list of character or a string, informing us on what the state of the list. It's empty, so we are pattern matching this parameter to an empty list. And here we are pattern matching this parameter to an element, just only one element in the list. Here we are pattern matching a list that has 2 elements, exactly 2 elements. And here, here we are pattern matching, 2 or more elements. So that's the concept of pattern matching. So do you see that in action really quick? So you see this in action. We have our tel function that takes in a string and return another string. Or remember, string or list of character. So list of character like that. So the tel function, we know it will take one parameter because that's what the declaration specifies, and return another one. So with this, if we do it like this, we are taking the whole parameter, the whole list of characters. But in order to illustrate that very well, let me put a list of characters here. List of characters there. Okay, so here now we know that this is going to come in as a list of characters, and it could be in different states. It could be an empty list, and in that case we return empty. It could be one element exactly, and we pattern match it like this. So it's one element with an empty construct. So that's exactly one element. And we do. And we could even continue, to pattern match and go to 2 elements. That would be like this. Yeah, and then we do 2. And to end, you know, to make sure that, because when you're pattern matching, you want to make sure that you cover all the cases. So I stop here to 2 elements. So if I try to run this code, Haskell will complain to me that, hey, look, you pattern match, but you didn't consider all the cases. So in that case, I would do, if you get anything, you know, that is over 2, and that underscore there means anything, and then at that point you return so very quick. If we go back here and we share what I did there, the GHCL to get into the Haskell compiler, and we reload. It's all happy, and we do tell. We call tell with an empty list. Tell not in scope. Okay, so we get this saying the variable is not in scope, meaning that it can't see this tell. So at this point, I need to make sure that I load my file. That point, so if I do tell, and I pass it the first option, I get empty. So if I do tell with, let's say, 1, you know, trying to match this pattern, 1, and an empty list. Oh, yeah, it's telling me that it's not happy because I said it was a list of characters. How come am I giving him a number? So we just fixed that very quick by providing a character here. Remember, single quote. And now he's happy. He returns 1. So now if we call this with, let's say, a lot of things, that list of character, now we should get a lot. So that's about pattern matching. Any questions here?
Yeah, please. Looking at the other screen, right? Actually, so are the values, like the values that are being matched, actually being assigned to those symbols X, Y? Like, will you do something with the value of that first thing? Like in the case of like one thing.
Yeah.
So,
yeah, absolutely. You could. Are you done with your question? Sorry.
Yeah, no, that's the question. That's the question.
Yeah.
Like, is the value actually in the X and the Y, so that in that particular case, I could do something with it?
Yeah, absolutely. So let's do something simple here. If we do int, and we want to return int, something like that. So in this case, you know, when we get this, we can return empty, because we'll return 0, right? And here, what we could do is, in this case, we know we have exactly 1 element, so I could return 1. But let's say we have some strange requirement that we need to add this 1 to this value we got from here, right?
Yeah.
And then in this case, I would do something like plus X. Does that make sense?
Yeah, that was my question.
Okay, great. A good question. So very quick, let's move on. So much content to cover. So that was about pattern matching. So now we have another construct in Haskell, which is called guards. Really what it is, it's, I would say, another way to really pattern match, but in a very elegant way. If you notice, like here we have our function, BMI tell, and it takes a type variable. You know, it could take a lot of things there that are conditioned by this, or constrained by real float. So I can see this as something with a decimal part. So maybe it could be a float or a double. And now over here, sorry, we return a string. But look what's happening here. So we don't even have an equal sign after we call by the name of our function. We pass in the first parameter that is specified there. We don't have an equal sign. We just start like mapping or pattern matching or using words to check the value of this. So we are actually checking some properties of this value here. So let me just demonstrate that. I'll just save some time. Copy this. It's really tedious to go in this. I hope I figure it out by the next thing. So let's get this bigger. So what's happening here, so if I do that, what's happening here is that in Haskell, look over here, we define this function declaration there, and here it's definition. And after you pass in the parameter, there's the sign equal before you start like doing your calculation. But with this Wada construct, you don't have to do that. So once you have these parameters, you just start adding your Wads and saying, adding some property to this. So in this case, we are checking that the, what is this? The BMI, you know, when they divide your, multiply your weight by something and they divide it somehow to figure out if your height and your weight are fine. This is the stands for that. And it's checking whether you are, you know, your weight is inferior or equal to 18.5 and so on. So when you do that, and then here after equal, you implement your result. So again, Haskell asks a great question when in this case, he asks whether we could use this X that is pattern match in this definition. Yes, it's the same thing here. So this BMI could be used here, you know, in a way like something like this, plus show being a function that takes, you know, things and convert them into strings. Yeah, so that's the other way to pattern match, but its specific name is Wads. Yeah, you are building your Wads. And this is the terminal case, meaning it covers everything you haven't covered here. That does not fall under this one, will fall under that otherwise. Any questions? Okay. So again, here's one example, my max. So there we're just using a Wad and saying if I have A and B, if A is superior to B, and then the max value out of these two is A. Otherwise, my max value is just B. And we'll come back to this type class. Just a hint, I is a type variable. And you see there's actually a great constraint because it's saying that I must know how to order himself for you to use the superior operator, which is another function, but we'll get to that. So the where construct gives you a way to define your variables after using them. So if we go back to this function, we see that we modified it and now it takes like a weight and a height. And here we are just using this BMI that we don't know where it's coming from. It's not a parameter that we entered there. But the where construct allow us to reference back to BMI by giving it that value, so that formula. So this is something really cool in Haskell. You can focus on the higher level code you know, just writing stuff like that and knowing that the BMI will be calculated like this. And just at the end, when you're done actually implementing your function with the where construct, you can, you know, give a value to this because it will be compared to that. So, any questions on this? Okay, no. So the let-in construct. So in many languages, you need a way to declare a variable, and Haskell has this let-in construct, which actually allows you to, you know, assign a value to a variable or define your variables. But then after the in construct, you use them for something. So I'm going to copy this and we're going to run an example to make sure that we're all getting this. So go into the repo. So paste that instead into my file. So I'll paste that there and I will format a little bit. Okay. So here you see our function. I'm sure how to spell this. Cylinder. Yeah, I think it's that. And then cylinder is taking 2 parameters and it's returning another one. So here we define the function. It's taking those 2 parameters of type A, R is of type A, H is of type A, and remember it's constrained by real float. And in here, you know, we use let to define a variable within our function. So we have the side area. You know, when you have a cylinder, you want to calculate its volume or whatever. I'm not sure what this formula is actually. But anyways, you can declare like a set of variable. I could have added another one, like my val equal 9 and so on, as many as I want. And then in the in expression, I do some calculation. So I declare, I define my variable there, and now I'm using to do some calculation in here. So is there any question on this? I guess not. So let's, okay. What, is there a question?
No, saying everything is okay for me. Okay,
cool. Now, another construct in Haskell is case expression. Case are really, I would say to me, they look more like if or a quad, because what actually happens is you have case, you have your expression, which could be a function call that returns something. And you are trying to figure out if that's something that was returned here, because each expression returns something. You know, you pattern, there's a pattern here. Does this match this pattern? In that case, you run this block of code. Does this match this pattern? In that case, you run this block of code, and so on. So as an example, we have the function here called describe list, which is about getting a list and you know, and adding it to, you know, figuring out whether it's empty or not. But the beauty of Haskell here is that, you know, I start by writing my answer because I will return a string. So the list is, you know, I am using the ++ operator. Remember, this ++ operator takes 2 lists of characters and combine them together. So ++. But given that I want to check whether my list is empty, in that case, I will be returning empty. So I'll be getting the list is empty. because I have plus there and empty there. The other, way is like my list has exactly one character, and then my answer will be the list is this result will be returned a singleton list, and anything else will be a longer list. So this underscore, remember, means anything else. So the case is just using this variable that we enter, access, in this case, a list of things, a list of strings, character, I mean, and figure out if they're empty, if it's one element, if it's a multiple elements. So, and that's what it does. Is there any question here?
I just want to ask, are we covering all the 30 slides today? Because it looks like we have already run down 3 hours.
Yes. So I think we'll just probably, I will invite you to try to read the how can I say it, the remaining topics, and tomorrow we'll come back very quick to that, and then we will do a lot of exercise to make sure that you get the context. But very quickly before we wrap up, I want to make sure that I see this lambda expression session, and at that point we can come back tomorrow with the next point, which is recursive function. So a lambda expression, which comes from mathematics, lambda calculus, what it really is an anonymous function, which means that a function without a name. If you remember, so far we've been defining our functions, giving them names, like in this case, that has a name. But a lambda expression is actually a function that doesn't have a name. And its syntax looks like this, or like this. Why write a function that doesn't have a name? When we talk about something called higher order function, that takes functions as parameter in this case, and sometimes the functions that we take don't need a name. They are just used within another function, so you don't need to give them a name, and you just write it using lambda expressions, and it's really convenient so that you keep your code like short and tight. So if there are questions, very quick questions, I can answer them. Otherwise, we can take a break and come back here tomorrow to wrap this up and get to exercises. Any questions? I will take that as a no. Well, guys, thank you very much for being here. I know it's a little bit over things that as we do this more and we get more in details into our meetup and our Discord that we'll be setting up, and give you some guidance on specific books to follow. And as we meet regularly to talk about like specific subjects and a concept and focus on them, we will get through this. But I'm definitely conscious of the fact that this is a little bit overwhelming.
Mm-hmm.
Nana Safo, are you trying
that would be great
to talk?
Yeah, I'm just saying that would be great. With the Discord and the books, I think that would be a great guide in addition to the teachings.
Yeah, absolutely. And I invite you to, you all got an invitation email with the links that take you to all these documents.
Yes,
Look at them.
that's true.
on your own free time, and we'll come back to it tomorrow.
Sure, exactly.
All right, thank you.
Haskell? Yeah, thank you, Richmond. Haskell, did you have something to say?
No, just thanking you. Thank you very much for sharing your knowledge and for setting all of this up. Thanks to Wada for setting all of this up. I think that I benefited a lot, and I'm really looking forward to what we can use all of this to do soon. So,
Yeah,
Absolutely.
really waiting for the practical aspects, the use cases.
Great.
Yeah.
I wrote that down. Okay, guys, I will give it back to Megan to close the session if she has a word to say.